From 150 million kilometers away, the sun appears as a perfect sphere of light, constant, unchanging, and brilliantly bright. But up close, the surface tells a different story. The sun is no serene orb. It is a roiling, churning sea of plasma, a place of violent storms, magnetic fields, and eruptions of energy more powerful than anything we can produce on Earth. Among the brightest and most active areas of the sun's surface, we find an unexpected feature: dark spots. These are sunspots, small, cool patches on the solar surface that appear dark only because they are slightly less bright than their surroundings. Though they may look like minor blemishes, they are in fact profound clues, markers of deeper processes shaping the very heart of our star. What makes a sunspot dark? It's not because it's cold, far from it. Sunspots typically measure around 3,800 degrees Celsius, which is hotter than the surface of a welding torch. But that's significantly cooler than the surrounding solar surface, which blazes at around 5,500 degrees Celsius. The temperature difference and the resulting contrast in brightness makes these regions appear dark to us. If you could somehow isolate a sunspot in space, away from the blinding brilliance of the photosphere, it would still glow red hot. It's all a matter of perspective and of the forces behind their formation. To understand sunspots, we have to journey deep into the sun's interior, where temperatures soar into the millions and hydrogen atoms are squeezed and fused into helium, the process that powers the sun and fuels all life on Earth. Within the outer layer of the sun, known as the convection zone, hot plasma bubbles upward, releasing heat and light, then sinks again after cooling. But this rising and falling plasma doesn't just transport heat. It also helps generate and twist the sun's magnetic field. The sun's plasma is electrically charged, and as it moves, it generates magnetic forces. These fields can loop, twist, and tangle, especially due to the sun's differential rotation, where the equator rotates faster than the poles. Over time, the magnetic field becomes unstable and begins to rise up, breaking through the solar surface in highly concentrated regions. When these magnetic field lines burst through the photosphere, they disrupt the convection of energy in that region, temporarily preventing heat from rising. As a result, the surface cools slightly and a sunspot forms, an outward sign of inward complexity. These sunspots often appear in pairs or groups, connected by enormous magnetic arcs that can extend far into the sun's atmosphere. One spot represents a magnetic north pole and the other a south. Between them, glowing arcs of charged particles, called prominences, flow along the magnetic field lines, creating some of the most beautiful and dramatic structures in the solar system. Long before the invention of modern telescopes, early astronomers tracked the slow motion of sunspots across the solar surface. In the early 1600s, Galileo Galilei, using a simple telescope, drew careful sketches of sunspots and noticed something strange. The spots moved from east to west over several days. This was one of the first clues that the sun rotates, not as a solid body, like Earth, but as a giant ball of fluid plasma. At the equator, it spins faster, completing one rotation in about 25 Earth days, while at the poles, it takes more than 35 days. This uneven spinning, or differential rotation, plays a central role in the creation and destruction of magnetic fields that lead to sunspot activity. Over time, scientists noticed another pattern. Sunspots weren't just scattered randomly across time. They appeared in cycles. Every 11 years, the number of sunspots increases, reaches a peak, then fades again. This is known as the solar cycle, and it's one of the most critical aspects of solar science. During the solar maximum, sunspots are plentiful. Solar activity intensifies, and the sun releases more ultraviolet radiation and solar wind. Then, during solar minimum, sunspots become rare, the sun calms, and Earth experiences fewer space weather effects. But beneath this apparent calm, the sun's magnetic field is undergoing a massive transformation. At the end of each solar cycle, the sun's magnetic poles flip, north becomes south, and vice versa. This magnetic reversal is one of the most powerful and mysterious natural processes in the solar system. Sunspots are not only surface features, they're often the sites of intense solar storms. Magnetic field lines above sunspots can become so twisted that they snap, releasing tremendous energy in the form of solar flares and coronal mass ejections, CMEs. These eruptions can hurl billions of tons of solar material into space at millions of kilometers per hour. If one of these storms is directed toward Earth, it can arrive in just a couple of days, or even hours, and wreak havoc on modern technology. Communication satellites can be knocked offline. Power grids can experience blackouts. GPS navigation can become inaccurate. Even astronauts aboard the International Space Station must take shelter to avoid exposure to high-energy particles. That's why tracking sunspots is not just about science, it's about safety. Fortunately, Earth has a built-in defense. Its magnetosphere, a protective magnetic bubble that shields us from most solar radiation. When particles from the sun strike this field, they're deflected toward the poles, where they collide with atoms in Earth's atmosphere. The result? The beautiful, glowing displays we call auroras, the northern and southern lights. They are, in a way, Earth's own visible reaction to sunspot activity, a cosmic light show triggered by magnetic drama unfolding millions of kilometers away. Today, scientists monitor the sun using a fleet of space-based instruments. The Solar Dynamics Observatory provides near-continuous, high-resolution images of sunspots and solar flares. The Parker Solar Probe, launched in 2018, is flying closer to the sun than any spacecraft in history, diving into the corona, the outermost layer of the solar atmosphere, to study how magnetic fields behave in real time. Every bit of data we collect from sunspots, their number, size, location, and movement, helps us understand the sun's cycles, forecast space weather, and even learn more about stars beyond our own. The story of sunspots is a story of curiosity, from early astronomers peering through handmade telescopes to modern spacecraft flying into the sun's atmosphere. What began as mysterious dark patches has become one of our most important tools for studying stellar behavior. And the journey is far from over. As our tools grow more sophisticated and our models more precise, sunspots continue to reveal secrets, not only about the sun, but about the nature of stars, magnetic fields, and the invisible forces that shape the universe. In the end, sunspots are more than marks on the face of the sun. They are the visible fingerprints of a star in constant motion, signs of energy, tension, and change. They are portals through which we glimpse the invisible machinery powering our solar system. To study a sunspot is to read the language of the sun, written not in words, but in magnetism, plasma, and light. And each one, no matter how small, brings us one step closer to understanding the greatest source of energy we know.